on a set. So we have a set S and a binary operation on S. Think addition, multiplication. So what is a binary operation? The input is a couple. You need two things for the input, and the output is one object. So if A and B are in S, then A star B is an element, not necessarily of S, but it's some kind of object. So the five properties that we're going to study is the closure, associativity, commutativity, identity, and inverse. Let's quickly go over closure again. We say that a set S and an operation star is closed if A star B is back in S for all A, B, and S. Typically, S is described as the set of all objects with a certain property or that look a certain way. And then the question is always, if A and B have this property, will A star B also have that property? Right? And so we did some examples. The standard examples are the numbers. We have natural numbers, integers, rationals, reals, and complex numbers, and then the matrices. And it turns out under addition, everything was closed. But for the integers and for the real numbers, this is an axiom. We have to accept that. However, for the rational numbers, we had to prove it because the rational numbers were defined as in terms of integers. But we were able to prove that they were closed. Okay, then the real numbers again were closed. That was an axiom. And the complex numbers, we had to prove it because a complex number is defined in terms of real numbers. And so the big takeaway was that it was all closed. The only operation so far that we came up with that was not closed of standard was the natural numbers under subtracting is not closed. Because we could subtract two natural numbers and not end up with the natural numbers. But everything else was closed. Right? Then we moved on to the associative property. Associative property is saying that if you have three elements A, B, C, it doesn't matter where you put parentheses. A star B star C is A star B star C. So you really have to think a little bit like a computer. You only know how to add two numbers, not three. So how would you add three numbers? Well, you add two at a time. Okay? And one of the practical application of associativity is that you don't need parentheses because you can't go wrong. The real numbers and the integers under addition were associative. But for the real numbers, this is an axiom. The integers, yeah, you could say it's an axiom, but it turns out that associativity is an example of a property that is inherited. What does inherited mean? Suppose that you have a set and an operation that is associative. If you pick any subset of that set S, then T will also be associative. You might wonder, why does that work for associativity and not for closure? Roughly speaking, any property that is true for the big set is true for a subset. It is inherited, but it might not be the property that you want. So let me show that about associativity. So associativity is inherited. So here, suppose that we have T is a subset of S. If S under star is associative, what does that mean? It means that for all A, B, C, and S, A star B star C is equal to A star B star C. And what is the property that is inherited is always what comes after the for all. This here is inherited. Okay? So what does that mean? So for all A, B, C, and T, this property is still true. That means T is associative. But closure is not inherited. Let me write down why. So S under star is closed means for all A, B, and S, A star B is back in S. What is the inherited property? Whatever comes over here, this is inherited. So for all A, B, and T, we have this property as well. A star B is back in S. But that is not saying that T is closed. This does not mean that T under star is closed. Because for T under star to be closed, you would need that A star B is back in T, not S. So there's a little bit of confusion about inherited. In any property that comes after the for all is inherited, but it might not be what you want. Typically, if this property mentions the set, it's not going to do you any good. If it doesn't mention the set, like in associativity, there's no mentioning of S in here, then it will help you. Okay, so back to the presentation. Since we are accepting as an axiom that the real numbers under addition are associative, that means anything that's part of the real numbers is also associative under addition. The integers, the natural numbers, the rational numbers, all these guys are associative under addition. So then the next big one is the complex numbers. For the complex numbers, we have to prove it. So we start with picking three complex numbers, write out how they look like. If x, y, and z are complex numbers, how can we write x, y, and z then? So what could we use for x? A plus bi. For y, I can use something else, right? I cannot use a and b anymore. And z can be e plus fi, where a, b, c, d, e, and f are complex numbers, are real numbers, right? Now we need to again think like a computer. You can only add two things at a time. So plenty of parentheses. So what if we first add x and y and then z? X is a plus bi, y is c plus di. I'm going to use parentheses here, but that's not really needed, just for clarity. So that's x plus y, and then we add z to it. So first I add these two. How do we add these two complex numbers? Add the real part, so we get a plus c plus b plus di. Okay, so that's the first complex number. Now we need to add e plus fi. Right? Can you give me the correct real part in the final answer? But remember, use parentheses because you can only add two things at a time. What is the real part now? So what will my final answer be? Yes, Carrie, but you're adding three things there. A plus B plus E. I don't know how to add three things. So there should be more parentheses in there. So if I write A plus C plus E, I'm skipping a piece. And here B plus D plus F, that's not what a computer would see. Because the computer sees A plus C as one number. It's A plus C, and you add E to it. And then here for the imaginary part, we got B plus D, and then we add F to it. However, if we would add them the other way, first Y plus Z, so we get C plus DI plus E plus FI. First, I gotta add Y and Z. We do this by adding the real parts and the imaginary parts. And now we gotta add them again. So can you give me the real part of this using the correct parentheses? So the complex number A plus BI, and you add the complex number C plus I. So A plus C plus E, and then B plus D plus F. Viewing C plus E and D plus F as one number. All right, so the question is, are these two things the same? Well, two complex numbers are the same if and only if their real parts are the same and their imaginary parts are the same. So is this equal to this? And is this equal to this? So I'm going to write, I'm running a little bit out of space here. So x plus y plus z is equal to x plus y plus z, since a plus c plus e is a plus c plus e, and the other property. Now, why is that a plus c plus e is the same as a plus quantity c plus e? What are we using there? It's not commutativity. So a plus c plus e, it's associativity of the real number. So let me go all the way up here. Since the real numbers under addition is associative. It's for sure properties of the real numbers, but in this case, it's exactly the property that we're trying to prove for the complex numbers. That's the one we need. Okay, so these are kind of proofs that you should be able to write down that the complex numbers under addition are associative. Start with three complex numbers, add them in two different ways, and explain why you get the same answer. So the good news is the complex numbers are associative under addition. What else do we have? The other nice operation is multiplication. So is it true if A, B, C are are real numbers, is A times B times C the same as A times B times C? Do you think that that's true? So that we don't need parentheses for multiplication? Yes. In fact, any nice operation is associative. But why is it true? That's an axiom. We just got to accept that for the real numbers. Huh? But if it's true for the real numbers, then it's true for anything that's a part of the real numbers. So that means the natural numbers, the integers, and the rational numbers under multiplication are also associative. But the next one, the complex numbers, we would have to prove. It is associative. So let me write that down already. It's associative. But it would be quite a lengthy calculation. So it's something like this. Let x, y, z be complex numbers. Then, if I make it a little shorter, what is x times y times z? A plus bi times c plus di times e plus fi. And then if you have enough patience, you work this all out. And similarly for x times y times z. A lengthy calculation and properties of the real numbers show that they are the same. That x times y times z is indeed x times y times z. It's not that it's very bad. I just don't want to spend too much time on this. Right? But you just have to work it out. Why is it more work than the addition? Well, it takes more time to multiply two complex numbers than it does to add two complex numbers. Okay, so our numbers under addition and multiplication are all associative. Can we come up with an operation maybe that's not associative? Oh, let me first do the matrices. Right? Matrices under addition and under multiplication, let me write that both of them are associative. Roughly speaking, if something is called an addition or a multiplication, it should be associative. But let me show this partially for the addition. So you would pick three matrices. And then you would calculate it in two ways. So A plus B plus C. Let me just write it A11, A12, A21, A22 plus something similar for B. B11 plus, and then something for the C. Can you give me the correct first entry here in A plus B plus C? Again, using all the correct parentheses. Perfect. So first you add A and B, and then you add the C to it. But for A plus B plus C, you first have to add the B and the C, and then the A to it. But they are the same because of our under addition is associative. So it's not bad, but you just got to do this 4 times for each entry. But the matrices under addition, that's associative. The matrices under multiplication, weirdly enough, maybe, is also associative. But if you thought that it was a lengthy calculation to show that the complex numbers are associative, the matrices, it's a lot worse. This is a very lengthy calculation. Is there maybe an easier way? Yes, using something called sum notation, but that is definitely not the topic of the cset. Okay, but so the good news is our numbers and our matrices under addition and multiplication are both associative. Huh? Could it ever be that there's an operation that's not associative? Sure. If you look under subtraction, do you think that subtracting is associative? Do you need parentheses when you subtract? So when subtracting, do we typically have to be careful about parentheses? Yes. So this is very unlikely. This is not associative. And that means we should be able to come up with an example. And unless you pick some really unlucky numbers, 1 minus 2 minus 3, that's minus 1 minus 3 is negative 4. But 1 minus 2 minus 3 is 1 minus negative 1 is 2. Not the same. Right? So not every operation is associative. Addition and multiplication are. Okay, so we got 2 out of the 5 properties done. Closure, associativity. The next operation or property that I like to look at is the commutative property. Why? Because it helps to look at identity and inverses if you already know your commutative. If you're not commutative, then there's nothing to do about it. So what is the commutative property? We say that S star is commutative if the order in which you operate does not matter. So if A star B is B star A for all A, B, and S. Again, commutativity is an example of a property that's inherited because, so for all A, B, and S, A star B is B star A, this is what is inherited. There is no mentioning of S in here, so that means if it's true for one set, it's true for any subset. So Commutative properties. Let's have a look again at our numbers and our matrices. So associativity and commutativity are basically the only properties that are inherited. The real numbers under addition. So is it true that if A and B are real numbers, is A plus B equal to B plus A? That is yes. So it is commutative. Of course, my question is why? Well, it's an axiom. But because it's true for the real numbers, that means it's true for anything that's a part of the real numbers. So the natural numbers, the integers, the rational numbers, they're all commutative under this. Okay? It's true for the odd integers, whatever subset of the real numbers under addition is commutative. But there's one set bigger out there, the complex numbers. For the complex numbers, we're gonna have to prove it. So we pick two complex numbers. Let me immediately write them as a plus bi and c plus di, be complex numbers. So that means a, b, c, d are real numbers. Then what is x plus y? That's a plus bi plus c plus di. The way we add complex numbers is we add the real parts, we add the imaginary parts. We also add them the other way and see if we get the same answer. So that's c plus a plus d plus bi. And then the question is, did we get the same number? Well, two complex numbers are the same if and only if the real parts are the same and the imaginary parts are the same. So let me write that x plus y is y plus x, since a plus c is c plus a, and b plus d is d plus b. And why is this true? Commutative property of which set and which operation? The addition of which set? Not complex numbers. What kind of numbers are A, B, C, and D? They are real numbers. We're trying to prove that the complex numbers are commutative under addition, and we're using that the real numbers are commutative. So we can now write, yep, the complex numbers under addition are commutative. Right, so that takes care of the addition. Let's have a look at multiplication. Again, the same thing for the real numbers. If a and b are real numbers, is a times b equal to b times a? The answer is yes, but it is an axiom. So the real numbers under multiplication are commutative. That means that it's true for natural numbers, integers, rational numbers. We don't need to prove that. But for the complex numbers, we're going to have to prove it again. So, do you think that the multiplication of complex numbers is commutative? Correct, it is commutative. So we, again, do our standard X and Y be complex numbers. So A, B, C, D are real numbers. And we start calculating X times Y. So that's A plus BI times C plus DI. Yes, you FOIL everything. Can anybody tell me what the real part will be when you FOIL out A plus BI times C plus DI? Hmm? We have to really FOIL it, so let's maybe spend the time on there and do that. So the way we multiply complex numbers just for A times C, A times DI, ADI, B times BI times C, we can write it as BCI, but the last part is BI times DI, which is BDI squared. And then we got to remember I squared becomes -1. So what is the real part here then? AC minus or plus BD times -1, so minus BD. And the imaginary part is AD plus BC. If I would give you two actual complex numbers, Carrie, you wouldn't have any problems. It's just because there's A, B, C's, and D's here that it becomes a little messier. Okay, that's X times Y. Now we look at Y times X. C plus DI times A plus BI. We do the same thing. We FOIL C times A plus CBI plus DIA, that's DA, and then the I in the back, plus DIBI, that's DBI squared, and I squared is still -1. So the real part this time is CA minus DB, and the imaginary part is CB plus DA. And the question is, are these two things the same? So is this equal to this? And is this equal to this? So I'm just going to write, so X times Y is Y times X. Since AC minus BD is CA minus DB, and AD plus BC is CB plus DA. And this is properties of the real numbers. But we're actually using quite a bit of them. Can you see some of the properties that we're using of the real numbers to conclude that AC minus BD is CA minus DB? So can you pinpoint exactly which or property or properties of the real numbers that you're using to conclude that AC minus BD is CA minus DB? I see AC in the first one, but CA in the second. So we're using there that which operation is commutative, Carrie? The multiplication, yep. The multiplication of real numbers is commutative, so A times C is the same as C times A, B times D is the same as D times B. We're using that here as well for the second part, but you use something else. Namely, AD is the same as DA, and BC is the same as CB. But then we still have to switch the order under addition. That's the commutativity of the addition. So you're using the commutativity of both the addition and the multiplication of the real numbers here. But the good news is complex numbers under multiplication are commutative. So under multiplication and addition, all our numbers are nicely commutative. Let's have a look at an operation that's not commutative. Our standard example, the subtraction. This is not commutative. The order in which you subtract is important. 1 minus 2, for example, is not equal to 2 minus 1. 1 minus 2 is negative 1, 2 minus 1 is 1. They're not the same. But we will see another operation in a little bit that's not commutative, that's much nicer. Okay, so then let's have a look at our matrices. So this was here not commutative. Matrices, on the other hand, the addition is commutative. So you pick two matrices, you add them in both in either way and prove they're the same. So what is A plus B? Well, if we use our standard notations again, the first entry will be A11 plus B11, and then three similar other entries. What will B plus A be? First the B's, then the A's. And so we get B11 plus A11. And the question now is, are these two the same? Well, matrices are the same if all their entries are the same. So is A11 plus B11 equal to B11 plus A11? Yes. So A plus B is B plus A, since A1 plus B11 is B11 plus A11, and the other three entries too. And this is because the real numbers under addition is commutative. Again, that's standard one. The property that you're trying to prove is the one that you need from the real numbers. Right? So addition, and addition should always be commutative. How about matrix multiplication? When you multiply two matrices, does the order matter? No. So if A and B are two matrices, is A times B equal to B times A? Let's have a look. Suppose that A times B, A is the matrix 1, 2, 3, 4, and B is the matrix 1, negative 1, 2, 4. Can you tell me the entry first row, first column in this product? So when we multiply those two matrices, 1 times 1 plus 2 times 2, we get 5. And then 3 other entries. Now we calculate B times A. And indeed, the order should matter. And let's see what we get. 1 times 1 minus 1 times 3. 1 minus 3 is negative 2. So AB is not equal to BA. So this is an extremely important example. So it really is matrix multiplication is the standard example of a multiplication that is not commutative. So that's a very important example that you must remember the matrices. Yes, we've seen subtracting is not commutative, but as far as standard operations like addition and multiplication go, matrix multiplication is the standard example of a multiplication that is not commutative. Okay, we're doing good. We got 3 properties done already: closure, associativity, and commutativity. The last 2, identity and inverses, are related to each other. So what is identity? We say that a set S under an operation star has an identity if there exists an element in S such that when you operate by it, it doesn't do anything. So A star E is A, E star A is A. So it doesn't matter in which order you operate with an identity, it doesn't do anything. Of course, if your operation is commutative to begin with, then you only need to check one direction, because then A star E is E star A. Very important, the identity must be in your set. That's why identities are not inherited. Okay, so an element in your set that doesn't do anything. One can prove it's pretty straightforward that a set can have at most one identity. You cannot have more than one. So that's why we sometimes talk about the identity. All right. E is in abstract algebra a standard letter for an identity in general. But we'll see some other examples. So let's go back to all our numbers: the integers, the rationals, the real numbers, and the complex numbers under addition. Is there a number out there when you add it, it doesn't do anything? Zero. Now, because numbers have 2 operations, addition and multiplication, it's important to mention which one you really are talking about. So here, 0 is the additive identity, and 0 is in all those sets. It's an integer, it's a rational number, it's a real number, it's a complex number. However, you might notice that the natural numbers are missing. So the natural numbers under addition, there is no identity. Why is that? Isn't 0 the identity still? For that, of course, you got to be careful. It's not a natural number. 0 is not a natural number. The identity must be in your set. Okay, how about under multiplication? Is there a number out there when you multiply by it that doesn't do anything? 1. 1 is the multiplicative identity. Okay. In this case, I could add the natural numbers to it. The natural numbers under multiplication have an identity, namely 1. 1 is a natural number. But the natural numbers are pretty much going to be gone with our last property. Next, we're going to be looking at identity. So next is our matrices. For the 2 by 2 matrices, is there a matrix out there when you add it, it doesn't do anything? So I need a matrix this time. Sometimes you can set up equations to figure it out. So let me maybe do this once as scratch work. So I don't know what the additive identity matrix should be. So I'm looking for a matrix, and if I add something to it, I just get itself. What should I be adding? If I add 1, 0, 0, 1, that's not going to work. So what should I write here? Well, because we're adding component-wise, a plus whatever this thing is should just be a. So that thing should be 0. The 0 matrix is the additive identity. So the 0 matrix 0, 0, 0, 0 is the additive identity. When you add it, it doesn't do anything. How about under multiplication? Is there a matrix out there when we multiply by it, it doesn't do anything? Let's check it. A, B, C, D times 1, 1, 1, 1. What is the entry in the first row, first column? A plus B. So let me use some color here. 1 and 1. So it's A times the 1 plus B times, you guys told me 1 as well. Now, that doesn't work, right? Because that's too much. What should I get? I want this thing to be just A. Should be A. So the A times 1 is correct. But by what should I multiply my B to make sure that it disappears? Has to be 0. This has to be a 0. And then it's not too hard to see. This guy has to be 0, and this guy has to be 1 again. We've seen that matrix before. What did we call before the matrix 1, 0, 0, 1? What name did we give that? We call that the identity matrix. Why? Because it refers to this operation here. So I'm going to say this, use the same name, the identity matrix, typically denoted by I, which is 1001, is the multiplicative identity. But because the multiplication of matrices is not commutative, that means you have to check both sides. So yes, it turns out when you work this out that you get A, B, C, D. But if you multiply it the other way, you also get A, B, C, D. So the identity matrix, if we go back to the numbers, the identity under addition was the number 0, the identity under multiplication was the number 1. Now for matrices, under addition it's the 0 matrix, and under multiplication it's what we call the identity matrix, and there's not really any obvious reason why it is 1, 0, 0, 1. But by trial and error you can come up with it. So the 0 matrix is the generalization of the 0 number. The identity matrix is the generalization of the number 1. Okay, so last property. Now that we have identities out of the way, we can talk about inverses. You cannot talk about inverses unless you have an identity. You always have to have an identity before you can talk about inverses. So suppose that the set S and the operation star has an identity. And you pick an element in your set S, A. We say that A has an inverse with respect to star if there exists an element, call it B, such that A star B and B star A get you the identity. So the identity is that element when you operate by it, it doesn't do anything. The inverse, when you operate A with B, you get back to the identity. In that case, we say that B is the inverse of A, and we denote it by A to the power negative 1. But you should really pronounce it as the inverse of A. Let me quickly do two examples. For example, the real numbers under multiplication. What is the inverse of 2? The identity was 1. So by what do you need to multiply 2 to get back to 1? 1/2. And what would be another notation for 1/2? Is 2 to the negative 1. But what if I'm looking under addition? What is the inverse of 2 this time? Well, for that, you need to first know what was the identity under addition. So the identity is that element when you operate, when you add it, it doesn't do anything. What is the identity? 0. So what is the inverse of 2? What do you need to add to 2 to get to 0? Correct. -2. And so you wouldn't write this as 2 to the -1. So in general, if you don't know if your operation is addition or not, the inverse of a is denoted a to the power -1. But if you have it under addition, then you write it as -a. Now, let me first put this. So here you should pronounce this guy as the inverse of a. How do we pronounce this? We all say it, but that's not really the correct way of saying it. We all say -a. But what if a is a negative number? Perfect. This is called the opposite of a. Huh? So inverse of a or the opposite of a under addition. Okay? So that one element may have an inverse while another element does not have an inverse. We say that S has the inverse property if every element in S has an inverse. And if S under operation star is commutative, you only need to check one side, of course. But again, it's very important to realize that this is just a notation. It's a very good notation. We will see in all our examples that this behaves like -1 times a. But in general, it's just the opposite of a. Okay? So let's go back to our standard examples. Numbers under addition, numbers under multiplication, matrices under addition and multiplication. So let's look at the set S0, 1, 2. Yeah. So why do I pick 0 in here? Well, this set has an identity. What is the identity for the set S under addition? So this is the natural numbers where we add 0 to it, the positive integers. What is the additive identity here? So it's a number when you add it, it doesn't do anything. That's 0. So now do we have inverses? So if you pick an element in S, does there exist another element in S? So very important, the inverse has to be an element in your set. So if you pick an element in this set, does there exist another element in the set? When you add them, you get to 0. The answer is no. Can you give me an example, Carrie? -1 or -2. Any element like 2 is an element in S. There is something when I add it to 2, I get 0. It's -2. But -2 is not an element in S. So we have no inverses. They're not back in our set. That's why we're not going to talk about the natural numbers anymore. Under addition, they don't even have inverses. So it's really The numbers that we're looking at is typically integers, rational numbers, real numbers, and complex numbers. Okay, the integers. The identity is still 0. So if A is an element in Z, does there exist another integer B such that when you add them, you get 0? Yes. And in fact, what should B be? You might say, well, isn't that exactly the notation that you used before? Yes, that is the equation. So we have inverses. Let me write, we have additive inverses. But why? It's an axiom. We cannot prove it for the integers, but we will have to prove it for the rational numbers. So rational numbers, we also have additive inverses. So let's see if we can figure out what the inverses are. Now this might become like a very notational, but don't think of it as negative a, but the opposite of a. So let x be a rational number. So then I can write x as a over b, where a and b are integers, b is not 0. Can you tell me what the inverse of x is? Now remember, inverse of x should be a rational number, so it's an integer over an integer. So the opposite of x is, what is the numerator and what is the denominator? We're working under addition, Carrie. So I want something that I need to add to a over b, and I will get 0. Aha! The numerator is the opposite of a, and the denominator is still b. Why? A over b plus opposite of a over b is, put it on common denominator, we get 0 over b, which is 0. So that's why we write, what is the opposite of a over b? It's the opposite of a over b. That is the general notation. Now we came up with what the inverse of a over b, the opposite of a over b is. It's the opposite of a over b. So we do have additive inverses. Next, real numbers and complex numbers. Same thing again. So in the real numbers, we have additive inverses, but it's an axiom. The identity is still 0, so if a is a real number, then there exists a real number b such that a plus b is 0, namely b is what we call the opposite of a, but it's an axiom. The complex numbers still have additive inverses. Well, we have to prove it, so let x equal to a plus bi be a complex number. So a and b are real numbers. Can you tell me what the opposite of x is? Now, the opposite of x is what you should add to a plus bi to get 0. Now, in standard form, I need a real number plus a real number times I. What is the real part of the opposite of x? So the real part is the opposite of a. Uh, yes, but Maya, but I'm trying to get that formula in there. So what is the opposite of x? It's this guy here. It's the opposite of a plus the opposite of b times r. Why? If you add these two together, we would add the real parts, add the imaginary parts, and when you add a real number and its opposite, you get 0. And so that's why we write, what is the opposite of a plus bi? It's the opposite of a plus the opposite of b times I, and that's way too many plus minus, and we just write minus a minus bi. And so we came up with it just like we did for here. What is the opposite of a fraction? Take either the opposite of the numerator or the denominator, whatever you want. What's the opposite of a complex number? You take the opposite of the real part and the opposite of the imaginary part. And so nicely we have additive inverses. So then let's have a look at multiplicative inverses. For our numbers, what is the multiplicative identity? So think about what that means. The number, when you multiply by it, it doesn't do anything. 1. So what is the inverse of a number a? I need to multiply a by something, and I get 1. Well, there is one number out there, no matter how hard you try, you will never ever get to 1. Which number is that? So which number never has a multiplicative inverse? 0. Here, because you multiply 0 by anything, you get 0. You will never get 1. So instead of saying, well, the numbers under multiplication don't have inverses, we kick out the bad number. We say 0 is a bad number for multiplication, so we're going to kick it out. And a standard notation in abstract algebra when you do this is a star. So what is z star? That's z minus minus 0. So z where you get rid of 0. All the integers except for 0. So the identity is still 1. Do we have inverses here? So if you pick a non-zero integer, can you multiply it by another non-zero integer and get 1? What is the multiplicative inverse of 2? 1/2. Is that an integer? One half is not an integer. So here we have no multiplicative inverses. Yes, So 2 is an integer, and 2 times a half, or 0.5, is 1, but a half is not an integer. So the integers have no inverses. Now that doesn't mean that every single integer doesn't have an inverse. Can you give me an integer that does have an inverse? So an inverse that is an integer. That doesn't work for 2, but it works for 1, and there's actually another integer out there for which it works. Can you see it? Another integer, and the inverse is also an integer, -1. So, in fact, only 1 and -1 have a multiplicative inverse that is an integer. So this is a very important example. The integers under multiplication. So we've seen already a couple. Matrices under multiplication, not commutative. Integers under multiplication, you have no inverse. Okay? However, for all the others, it works out. So if you look at the rational numbers, kicking out 0, we have inverses. We have multiplicative inverses. So we would need to prove it. Let x be a rational number that is not 0. Then x can be written as a over b, where a and b are integers. B is not 0 in order for it to be rational, but a is also not 0 since x is not 0. What is the inverse of x? So what is the fraction that you need to multiply a over b by in order to get 1? B over a. Namely, a over b times b over a. How do we multiply fractions? You multiply numerator and denominator. You get 1 over 1. Oh, sorry. AB over AB. That simplifies, we get 1. So we have our very standard formula that we already knew from before. What is a over b to the -1? It's b over a. That's why these notations for inverses are so nice. They really behave like exponents or multiplying by -1. How about the real numbers? So if, let me use r for once, is a non-zero real number, does there exist another number out there, let's say s, such that when you multiply them, you get 1? The answer is yes. So we do have multiplicative inverses, but it is again an axiom. Now, can you tell me what the inverse of r is? So what is this number s? We typically have two notations for this s. So what is s in terms of r? We write 1 over r, and you also write this as in exponent form. That would be r to the power -1. Right? So, but these guys are really just notations. It's just a notation because what does that mean? 1 over a real number is just another notation for the inverse. So real numbers we accepted. Complex numbers, oh, we had to prove it. So complex numbers, again, we do have multiplicative inverses. But we have to prove it. So let x equal to a plus bi be a non-zero complex number. So that means a and b are real numbers, and somehow they're not both 0. Because if they would both be 0, then we would be looking at 0. X would be 0, and it's not 0. So what is x inverse? Huh? You write it as 1 over a plus bi, but that is just a notation. It's a complex number, so that means it should be a real number plus a real number times I. What did we do on day 1 to make sense of this? To see what complex number this is? What did we end up doing? Rationalize. I don't know if rationalize is the word for it, but you got to get rid of that I in the denominator. And how did we do that? So how do you get rid of? You multiply top and bottom by a minus bi. So we're not really multiplying by a minus bi, we're multiplying and dividing by it, so we're not doing anything fancy. We're multiplying by 1. I mean, we're not doing anything fancy in the sense that we're just multiplying by 1, but in such a way that it changes the way it looks. So now we can just multiply numerator 1 times a minus bi and also the denominator. Okay, does anybody remember or see what we get when you work out the denominator? So what is a plus bi times a minus bi? A squared plus b squared, perfect. So it is indeed, I really don't know what the word is, realized. We made it real, the denominator. Now, so what is this as a complex number? A over a squared plus b squared plus opposite of b over a squared plus b squared I. But there's no need to memorize this, but what we now see is that, yes, the inverse of a complex number is a complex number. It's a over a squared plus b squared plus the opposite of b over a squared plus b squared. And we're using here that we're not dividing by 0, that a and b are not both 0. So the real numbers have multiplicative inverses. We have accept that. The complex numbers, we had to prove it. So if I do a quick recap on numbers, integers under multiplication, no multiplicative inverse. But rationals, reals, and complex numbers, yes, we have inverses under multiplication. So in that sense, it's not so obvious what the difference is between rationals, reals, and complex numbers. They all seem to have the same properties. Okay, then back to our matrices. So matrices under addition and then matrices under multiplication. Right? So first we need to know the identity again. What was the additive identity? What was that matrix? When we add it, it doesn't do anything. The zero matrix. Okay. So do we have inverses? Well, could you tell me what you would need to add to the matrix A, B, C, D? And then when you add them, you're going to get the zero matrix because that's what inverses do, right? When you add them, you get the additive identity. So what should I write here? What should be the element first row, first column of the inverse? Ah, the opposite of A, the opposite of B, opposite of C, opposite of D. So that means every matrix has an inverse. So we do have additive inverses. And now we also have our notation, and again, it makes perfect sense. What is the opposite of the matrix A, B, C, D? It's the matrix opposite of A, opposite of B, opposite of C, opposite of D. It really is as if you were multiplying by -1. Because how do we do scaling multiplication? You multiply each component by that number. So that's why this is such a great notation for the inverse. It really is like you're multiplying by -1. So under addition, we have inverses. Ooh, nice. Okay, let's have a look on the multiplication then. What was the multiplicative identity? 1001. Ooh, I think we did this on day 5 or slash day 6. Does every 2 by 2 matrix have an inverse? We saw that not every 2 by 2 matrix had an inverse. In fact, a formula that you didn't need to remember, a 2 by 2 matrix, we had A, B, C, D has an inverse if and only if a certain number was not zero. Does anybody remember that number? AD minus BC. And what did we call that? That number AD minus the determinant. It determines if you have inverses or not. So, well, bad news. The matrices under multiplication, even if we kick out the zero matrix, we have no multiplicative inverses. Yeah, we expected that the zero matrix wouldn't have an inverse, but under all the other examples we did so far, zero was the only bad number. You kick it out, and all of a sudden you're good. So here's what we did under multiplication. We kicked out zero, we have inverses. We kick out zero, we have inverses. We kick out zero, we have inverses. Here, that won't work. So we do something else. We keep going like that. If there's a whole bunch of matrices that don't have an inverse, kick them all out. So the question there, or the notation that we use there, is not a star really anymore, but we call that GL to R. So what is the definition of GL to R? It's all the 2 by 2 matrices whose determinant is not 0. So it's all the ones that have an inverse. So all the 2 by 2 matrices that have a multiplicative inverse. You might say, well, that's kind of cheap. If you're only looking at the ones that have an inverse, of course they're going to have an inverse. True, but it's a pretty big set. And so I want to mention some properties of this. So properties of GL2R under multiplication. First of all, it is closed. Why is that? Well, let A and B be elements in GL2R. Then what is the determinant of AB? I mentioned it as a property. It's not an obvious property, but it's the determinant of A times the determinant of B. And this guy is not 0. This guy is not 0. So the answer is it's not 0. So AB is back in GL2R. The multiplication of invertible matrices is closed. It's of course associative because that's inherited. There is an identity, namely the identity matrix. And we have inverses because we only looked at the matrices that have an inverse. So we got 4 out of the 5 properties that we studied GL2R under multiplication has. However, it does not have the 5th property. What is the missing property here? We talked about closure, associativity, identity, and inverses. Which one is missing? Commutativity. So the multiplication of matrices is not commutative. Not bad, 4 out of the 5. But it turns out we got the best 4 out of the 5. Well, if you look at the integers under multiplication, you're close to your associative, you have an identity, you don't have inverses, but you are commutative. But it's much nicer to have inverses. Okay, so we're done with the biggest part of it. We're not going to see any new properties anymore tonight. But so we've talked about 5 properties: closure, associativity, commutativity, identity, and inverses. And we've seen that our numbers under addition have all those properties. Under multiplication, the integers don't have inverses. The matrices under addition, all properties. Under multiplication, it's not commutative, and not everything has an inverse, so you have to restrict yourself. So now we're going to put this together into special sets depending on which properties you have. And the first type of specialty is called a group. So what is a group? A group is a set G together with a binary operation, and it should have 4 of the 5 properties that we studied. It should be closed. It should be associative. There should be an identity, typically denoted by E, and every element in G must have an inverse in G, of course. So Those four properties, if you have those four properties, you are called a group. And it's okay if you have the fifth property, if in addition you have that it's commutative, the operation, then for some weird reason, we don't call it in group theory in a commutative group. We call it an abelian group for a Norwegian mathematician that looked at it. So if you would say the group is commutative, everybody will understand what you mean. But so a group is basically closed, associative, identity, and inverses. Now, why on earth would anybody look at this? So let me write here these four here. These are exactly the properties you need to solve a linear equation. Huh? So let's see this on the side here. Suppose I would tell you just, so we have G under star, and we want to solve for X in G, of course. So A star X is B, a linear equation. So A and B are in G, and we're hoping to find an X in G such that A star X is B. How would you solve this for X? Think about what you would do for numbers and then see if you can make sense of it. So what do you want to get rid of? You want to divide by A. We can't really divide by A. What if A is a matrix? So, but by what could we multiply to get rid of A? 1 over A inverse, A to the negative 1. So multiply both sides by A or star A inverse. So that only makes sense. You need inverses for that. Okay. I need to use my parentheses here because if I don't write parentheses, then this doesn't make sense. I don't know how to operate or multiply three things together. Okay. Next, why did we multiply by A inverse? Well, somehow it should disappear, right? Well, the first thing I need to do is put the A inverse and the A together. Which property says that I can switch these parentheses? That's associativity. So we're going to need associativity. Okay. Then if I multiply an element by its inverse, what do I get? The 1, but in general, it might not be the number 1. It could be the matrix 1, 0, 0, 1. It could be the matrix 0, 0, 0, 0. It becomes the identity. So we, of course, need identity, but we already knew this. You can't talk about inverses without an identity. Okay? Now, what does that property 1 have, or the identity? If you operate the identity with anything, what do you get? What is 1 times x? That itself. So we get x. Okay. And I asked to solve in G. So why is X an element in G? Because of closure. A inverse and B are in G. So if you use closure, then A inverse operation B is back in G. So the very natural way of solving a linear equation requires you to have inverses, be associative, have an identity, and have closure. That's, in my opinion, why, of course, we study sets that have these four properties, because now we can solve linear equations. Okay? So that is called a group. Well, let's have a look at our examples. I know this gets a lot of stuff in one day, but we're not seeing anything new anymore. We already know all the properties of our numbers under addition and multiplication and of the matrices. So we're just putting it all together and see what we have. So if we look under addition, we typically didn't have any problems. Like the integers, the rationals, the reals, and the complex numbers, we've proven that they have all five properties. It's closed under addition, it's associative, it's commutative, there's an identity and inverses. So we have an abelian group. But under addition, just the natural numbers, we had an issue there. What's the issue with the natural numbers under addition? No inverses. And also, what should be the identity under addition? The identity should be 0, and that's not a natural number, but you're absolutely right. There's for sure no inverses. So let me write not a group. However, it is closed, it is associative, and it is commutative. So it has those three properties going, but no identity, and for sure, no inverses. And that is really the reason why the natural numbers are pretty much not studied in terms of group theory. And it's just not. They're not very nice to look at. But under addition, the others, integers, rationals, reals, and complex numbers, they're all abelian groups. Okay, how about multiplication? Here, the rational numbers, the real numbers, and the complex numbers, we all had abelian groups. But what went wrong with the integers under multiplication? Carrie, now you can just repeat your chat. It is not a group, the integers. We have no inverses. But it is closed. It is associative. We have an identity. It is commutative. And we have an identity. Oh, we're one property away from being a group. So that is, I would say, standard example. The integers under multiplication, not a group. And then no distinction. So at this point, we cannot distinguish between the rationals, the reals, and the complex numbers based on only the addition or the multiplication. They all have the same properties. How about the matrices? Okay, the matrices under addition, nothing went wrong. So this was an abelian group. We had everything. But under multiplication, it went wrong real quick. We didn't have inverses. So that's when we looked at GL to R. And that became a group because here, GL to R under multiplication is closed, associative, there's an identity, and you have inverses. So you're a group. Ooh, but you're not commutative. So this is the standard example of a non-abelian group. Not commutative. But everything else goes right. Mhm. So very important examples again. The matrices under addition and multiplication. Okay, so that's a group. Okay, let's do. I got one or two exercises from the cset related to groups. So question 1 and question 12. Question 1. Use the table below to answer the question that follows. So we have a set M with elements A, B, C, D under operation add is defined by the table above. So what does that mean? For example, C operation D is D. C operation A is B. That's how we have to read this table. Which of the following is the inverse element for A under this operation? So they're saying here that A should have an inverse, and they're asking, what's the inverse of A? Is it A, B, C, or D? Very important. Before you can talk, or what is the idea behind an inverse? What should the inverse of A do? So let me maybe write this down here. Go to 1, but in general, it might not be 1. So what is the general term for 1 instead? That should be the identity. So that's what I meant. You cannot answer this question until you find the identity first, because I don't know what I should get. A operation, its inverse, should give me the identity. Well, I don't know what the identity is. So first we have to find the identity. What property does the identity have? So how can I look at that table and figure out, oh, that's the identity? When you operate an element with the identity, what do you get? Itself. That's the defining property of the identity. So can you now look at this table and tell me what the identity is? So it's that one element, when you operate by it, it doesn't do anything. That's B. The identity is B. Because A operation, which element gives me A? A operation B. Now we should check the others. B operation B is B. C operation B is C. D operation B is D. Yep, B is the identity. So now I can finally go back and find the inverse of A. A operation A inverse should be B. What is A inverse? It's C, because A operation something gives me B, that's here. It's C. A operation C is B. So first we figured out that B is the identity, then we figured out that C is the inverse of A. And you should check the other one. C times A should also be then the identity. C operation A is B. So yeah, the correct answer here is C. Okay, for everybody, you cannot talk about an inverse or find an inverse without finding the identity first. In words, and I find that very important that you understand that, the identity is that thing that doesn't do anything. You operate with the identity, you get it solved. The inverse is when you operate by your inverse, you get back to the identity. Number 12. Use the information below to answer the question that follows. So given z is a plus bi, z bar is a minus bi, where a and b are not zero, and the absolute value of z squared is a squared plus b squared, prove that z times z bar is absolute value of z squared. Step 1, z times z bar is a plus bi, a minus bi. Step 2, a plus bi, a minus bi is a squared minus abi plus bai plus b squared. Step 3, a squared minus abi plus bai plus b squared is a squared plus b squared. Step 4, therefore z times z bar is the absolute value of z squared. And they're asking us, so they gave us there in short a proof, and they want us to, which of the following properties is one justification for the simplification made in step 3. So first you should realize, what did they do here in step 3? And then which one of these properties best seems to justify that? In words, what did they do in step 3? But they simplified something, right? Two things canceled out. The minus ABI and the plus BAI canceled out. So which one of those four properties seem to best explain that they cancel out? Additive inverse. They are actually using another property, but it's not listed. Do you see which other property they are using? So if you don't look at step 3, let me say, what should I add to minus ABI to get to 0? So don't look at step 3, just look at what I wrote. Minus ABI plus, what should I write there so that equals 0? You would write ABI, but that's not what they wrote. What did they write? BAI. So why is this equal to BAI? The real numbers under multiplication is commutative. That's another property that is used, but that's not in the list. But it is another property that's used. You're using the inverse property of the addition and the commutative property of the multiplication. Okay, so let's maybe quickly go over this. This is a nice example. It's pretty much like that first question from the cset. So it is given that the real numbers, if you kick out -1, is a group under this very weird operation star. What is A star B? It's AB plus A plus B. And the question is, what's the identity element in this group G? What's the inverse of A1? And what's the inverse of A in general? So let's maybe, just to do an example, could you tell me what 2 star 3 is? It's 11. 2 times 3 plus 2 plus 3 is 11. So it's a weird operation, but 2 star 3 is 11. Okay? So first we're looking for the identity element. Which property does the identity element have? So let's call the identity element, I typically call it E. Then what property should it have? A star E should be A for all A. So now you typically have two possibilities. You keep it abstract A, or you just plug in anything for A and figure out what E should be. What is A star E? AB plus A plus E should be A for all A. Sorry, there's a typo there, it shouldn't be B. So could you solve this for E, and could you tell me what E is? I'm going to do it in general, but then also on an example. But now we're back to real numbers. So these are all real numbers. Could you solve this for for E? Let me maybe make it slightly less abstract. If this has to be true for all A, let me just use an example. Let's use 2. 2 star E should be a 2. What is 2 star E? Two E plus 2 plus E, and that should be 2. Solve. Now we are back down to purely the real numbers. Solve this linear equation. Has nothing to do with groups anymore. 2E plus 2 plus E is 2. What is E? We get 3E is 0. E is 0. The identity in this group is the 0 element, is 0. Could we have done this over here? Sure. We first see that the A's cancel out. So we get now the equation AE plus E is 0. We factor out the E. That means A plus 1 is not 0 since A is not -1. So E has to be 0. Either way, if this thing is a group, and they're telling us it is, the identity must be the 0 element. A star 0 is A for all A. Okay, so now what is the inverse of 1? I'm just going to do the inverse of 1. Inverse of 1, let's call it x. Then what is the property that the inverse of 1 had? when you operate 1 with x, what should you get if x is the inverse of 1? An element operation, its inverse is always the identity. Yeah. And what was the identity in this case? The identity here in this example was not 1, but was 0. So 1 star x should be 0, solve for x. What is 1 star x? So a star b is ab plus a plus b. So 1 star x is 1 times x plus 1 plus x. And that should be 0. Solve for x. What do you get for x? X is negative a half. So very weird. In this group, the inverse of 1 is negative a half. So my point with these groups is just like that first exercise on the cset. If they tell you it's a group, you can figure out the inverse, or you can figure out identity and inverses by just setting up an equation. The identity is that thing that doesn't do anything, so I just picked 2 here as an example, but you can pick whatever you want. 2 star e should be 2, solve for e, we got that e is 0. Inverse of 1, 1 star x should be the identity, which we figured out is 0. We end up that x is negative a half. So, very weird group here. Okay, so that was a group. The next topic, we're pretty much done, with general properties is rings and fields. You noticed in the examples that were very important for us, which are numbers and matrices, there were 2 operations involved: addition and a multiplication. And in terms of group theory, you only look at one. But for rings and fields, you look at both. So in order to get going with rings and fields, we have a set R with 2 operations, namely an addition and a multiplication, and they need to satisfy a whole bunch of properties. This might come over again as rather abstract, but it is a generalization of the integers. The integers are the standard example of what we call a ring. First, under addition, you're perfect. So the addition, you gotta be in a Abelian group. Remember, that's really 5 properties. The addition has to be closed, associative, commutative. There has to be an identity element, and every element must have an inverse. The multiplication, you only require 2 out of the 5 properties. The multiplication should be closed and associative. Right? So you don't require commutative, identities, or inverses for the multiplication. And then there is one extra property, something that relates the addition and the multiplication together, and that's called the distributive properties. Namely, A times B plus C is A times B plus A times C, and B plus C times A is B times A plus C times A. Those are the properties that you need for a ring. Some standard notations in a ring is that the additive identity we're just going to denote by 0. It's not the number 0, okay? Sometimes I like to call it 0R to indicate it's the 0 in this ring. It could be the 0 matrix. It doesn't need to be the number 0. The additive inverse of A is denoted by the negative A, but that is equal to the opposite of A. Just a notation. So to quickly recap, no problems under the under addition. 5 properties. 2 properties for the multiplication. Typically, if you have extra properties under the multiplication, then your ring has that name. For example, if the multiplication is commutative, you say that your ring is commutative. It doesn't refer to the addition because the addition was supposed to be commutative already. So similarly, if you have an identity, it's regarding the multiplication because we already know we have an identity under addition. Okay, so that is a ring. Ring 2 out of the 5 properties for the multiplication. What is a field? It's basically a ring where you have all 5 properties for the multiplication. So again, under addition, you're in a abelian group. Under multiplication, you are also in a abelian group. So yes, you have associativity and closure, but you must be commutative, have an identity, and have inverses, except, of course, for 0. And you still have the distributive properties. So a field, every ring is a field, but not every field is a ring, but not every ring is a field. The additive inverse of A is the opposite of A. Multiplicative inverse of A is A to the negative 1 over 1 over A. So let's do some standard examples that we've seen so far of both rings and fields. So the difference between rings and fields, in a field, your multiplication needs to have every property. For a ring, you only need 2. So every field is a ring. Let's do the standard examples. Let's look at our integers. Under addition and multiplication. Under addition, nothing went wrong. And any of the numbers, everything we have in a abelian group under addition. But the multiplication, sometimes things went wrong. What happened under the multiplication of the integers? We did not have all 5 properties there. Which one did we not have? So we were closed. Yep, we had no inverses. So that makes this not a field, but it is a commutative ring with identity. So, and the reason is indeed we have no multiplicative inverses. So it was one property away from being a field. But this is again a very standard example that you need to remember. Integers, it's a ring, but it's not a field. That's what people had in mind when they started studying these things, is generalizing the integers. However, how about the rational numbers, the real numbers, and the complex numbers? These are your standard examples of fields. And so you should know them. They are probably the only fields that you know: the rationals, the reals, and the complex numbers. And at this point, there doesn't seem to be a distinction between them. All right. Then there was one more missing, is the matrices. So what do we have for the matrices? Under addition, nothing goes wrong. Under the multiplication, a lot of stuff went wrong. Could you tell me? Let's go over the 5 properties of matrices under multiplication. It's closed and it's associative. Okay, so it's a ring. Is there an identity under the multiplication for matrices? So was there a matrix when you multiply by it, it doesn't do anything? It did have an identity. It was the identity matrix 1001. Okay, but not every matrix has an inverse, only those whose determinant is not zero. And was the multiplication of matrices commutative? No. So this is the standard example of a non-commutative ring. And it actually has an identity. With identity 1001. So if I can go back to my previous slide, you now know 2 examples of rings: the integers and the matrices. What's their difference basically is that the integers are commutative while the matrices are not. And then you have your 3 other numbers: the rationals, the reals, and the complex numbers, which are fields. That's it. Those are the ones that you should know very well. So for the last or the last part of tonight, I want to talk a little bit about the difference between the real numbers and the complex numbers. But first, I wanted to mention something, and these kind of properties seem so obvious, and yet when you try to prove them using the axioms, it's not so straightforward. So suppose that R is a ring. Then when you multiply by 0, you always get 0. Now that's the 0 in your ring. Okay. If you multiply any element in your ring by 0, you get 0. Now that sounds so obvious to us now because we grew up with that property. But once we think about it in terms of abstract algebra, this is not obvious at all. Because 0 comes from which operation? What does the 0 stand for? It's an identity, but under which operation? Addition. So what is the property that 0 has? When you add by it, it doesn't do anything. Why on earth would that have anything to do with multiplication? So that's what the weird part is here. 0 comes from the addition. Why would it have anything to do with multiplication? Well, when we go back to our ring, what is the only axiom or rule that involves both the addition and the multiplication? So here are those rules, which is the only one that involves both operations. Not associativity. Associativity only involves one operation. So associativity, A plus B plus C, we don't need parentheses. Same for multiplication. Correct. The only one that contains both is the distributive laws. So the reason why when you multiply by 0 you get 0 should come from these properties. That should be the reason why. Okay, so let's see if we can prove this using only these rules here. All right, so here we go. We pick an element in the ring. What I'm going to do now is I'm going to multiply A by 0 plus 0. I want to write 0R to really indicate this might not be the number 0, this could be the 0 matrix. I can evaluate that in two ways. First, 0R is the additive identity. So what do you get when you add 0R to anything? Is that anything? So what is 0R plus 0R then? Zero R. But I can also use the distributive laws to work this out. I get A times 0 plus A times 0. Okay? So I prove that this is equal to this. Just to make it a little easier, let me give that a name. A times 0R, I'm going to call this X. So what did we prove so far? X plus X is equal to X. I want to solve this equation for X. I'm going to add the opposite of X to both sides. I know I have opposites because under addition I'm an abelian group. I got to be careful. I got to write it like this. Here I can switch my parentheses. Why can I do that? Associativity. Okay, almost there. What do you get when you add an element and its additive inverse? When you add them, what do you get? Zero. So x plus 0 is 0. One last step. What is x plus 0? X plus 0 is x. So we have proven that x is 0. What was x? a times 0. So we've proven that a times 0 is 0. Something that we seem to know so well. If you multiply by 0, you always get 0. It follows from the standard properties of a ring from the distributive laws. Okay, so these exercises are a little bit more abstract, but so why do we do this? There's a lot of different structures out there, and it's not just the numbers or the matrices. And so in those very weird structures, you still have the property when you multiply by 0, you get 0. Okay, last topic of tonight, we'll see how far we get, is ordered fields. It's the difference between the complex numbers and the real numbers. I'm going to give you guys the definition of an ordered field, but you don't have to memorize all these rules. What does it really mean is we should a field is an ordered field if there exists a relation on F. I wrote it down almost like less than or equal to, because less than or equal to is a standard example of such a relation. And what do you want? We want meaningful inequalities. That is what an ordered field means. So whatever you think of on inequalities over the real numbers, that's what you should be able to do. So can you tell me something that you are allowed to do to inequalities? And we use that all the time to solve inequalities. For example, if you look at 2x minus 3 is less than or equal to 7. How would you solve this? You add 3. So the first thing that you wanted to do is, if you have an inequality, you're allowed to add the same thing to both sides. If A is less than or equal to B, then A plus C is less than or equal to B plus C. Okay, so we end up with 2x is less than or equal to 10. And then you divide by 2. Let's say for a second that we don't know how to divide by 2. Dividing by 2 is the same as multiplying by a half. Now, when do I have to be careful when I multiply both sides by an inequality by a number? If it's negative. So if A is less than or equal to B and C is positive, I'm not going to write bigger than or equal to because I only have less than or equal, and 0 is less than or equal to C, then A times C is less than or equal to B times C. So that's what I mean with meaningful inequalities. You can add the same thing to both sides, and you can multiply both sides of an inequality by a positive number. Okay, so here, that's what I would hope you can remember from this. That's really what we want. And now I'm going to give you the rules for an ordered field. Okay, so first of all, every element should be related to itself. This is called reflexive. If A is related to B and B is related to A, then A is equal to B. Third, if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. Does anybody know the name of that property? Transitive, very good. That is called transitive. So these are three properties that we want that seem very obvious about less than or equal to, right? The fourth property we want is that you can compare any two element numbers. So if you give me A and B, then either A is related to B or B is related to A. Okay. And then the fifth and the sixth ones are the ones we talked about. You can add the same thing to both sides of an inequality, and you can multiply both sides of an inequality by a positive element. Okay, so if this exists on your field, then you are called an ordered field. What's the standard examples of ordered field? The two standard examples are the rational numbers and the real numbers. Namely, standard less than or equal to has all these properties. So the rational numbers and the real numbers are ordered fields. So another way to think about an ordered field is that you have positive and negative elements and the standard properties of inequalities. Okay, so let me do a spoiler alert already. The complex numbers are not an ordered field. So that is one of the big differences between the complex numbers and the real numbers. The real numbers, you can have meaningful inequalities. You cannot have meaningful inequalities over the complex numbers. The complex numbers are not ordered. You can't talk about positive complex numbers and negative complex numbers. It doesn't make sense. Okay, so that's in a nutshell what we're heading for the last 30 minutes. I do want to prove that. You probably don't need to know the proof, but it should follow from these 6 axioms. That's it. Let's first prove the following property. If you have an ordered field, then 0 should always be less than or equal to 1. Now, you might say, isn't that obvious? Remember again, this is your 0 element and this is your 1 element. They come from different operations. 0 from which operation does 0 come? Addition. So the additive identity is somehow in an ordered field less than or equal to the multiplicative identity. Now, don't say that identity, that the 0 matrix is less than or equal to the identity matrix only if you are in an ordered field. So if you have meaningful inequalities in your field, 0's got to be less than or equal to 1. Let's see if we can prove this. Okay? So I mentioned here all the properties of an ordered field. And now let's prove that 0 is less than or equal to 1. Okay, so proof. Well, suppose this is not true. Suppose this is not true. Then 1 must be less than or equal to 0. Can you guys tell me which of those 6 properties I'm using to conclude that 1 is less than or equal to 0 if it's not true that 0 is less than or equal to 1. It's a little harder to see this one, but I have two elements in my field, 0 and 1. One of those properties says that I can compare them. One must be less than or equal to the other one. Which property is that? This is property 4. What does property 4 say? Either 0 is less than or equal to 1, or 1 is less than or equal to 0. It's got to be one of those two. And if we're saying, well, it's not this guy, well, then it's got to be that one. Okay? Next, I basically want to move my 1 to the other side. So what do is I add the opposite of 1 to both sides. Which of those 6 properties tells me I can do this? That I can add negative 1 to both sides, the opposite of 1 to both sides. Property 5. Okay, so, but what is 1 plus negative 1? That's 0. And 0 plus negative 1? That's just opposite of 1. Okay, so we're just doing calculate. Now I have a positive element. What can I do? I can multiply both sides of an inequality by a positive number. Here, I'm going to multiply the inequality 0 is less than or equal to negative 1 by negative 1. So we get that 0 times negative 1 should be less than or equal to negative 1 times negative 1. Which property is saying that? That I can multiply both sides by a positive number. That's by 6. Okay, now we work it out. What is 0 times anything? 0. We've proven that. You guys should try to prove on the exercises. What do you think the opposite of 1 times the opposite of 1 is? It turns out to be 1. Two opposites cancel each other out. But you have to prove it. Okay. Okay, that's good. Now what do we have? We started with 1 is less than or equal to 0. And also now 0 is less than or equal to 1. You could already say it's a contradiction, but if 1 is less than or equal to 0 and 0 is less than or equal to 1, that implies that 0 should be equal to 1. Ooh. Right there. Which of these properties tells us that? That's property 2. And that's a contradiction. Zero is clearly not equal to 1. Otherwise, when you multiply by 1, you should get itself. If you multiply by 0, you get 0. So the only field where 0 is 1 is a field with only one element. That's not really a field. Okay, so this might not sound very impressive, but it's a general property that we've proven now. If you have an ordered field, then 0 should always be less than or equal to 1. And now comes the kicker for tonight. Let's prove that the complex numbers are not an ordered field. That seems a lot harder than proving something is ordered, because in order to show that the complex numbers are not an ordered field, I have to show that no matter what I try, it will not work. And that is typically much harder than just coming up with one way that works. So let's prove that the complex numbers are not an ordered field. What is different about the complex numbers for the real numbers? So what would you say is the biggest difference between those two? So if anybody asks you like, what's different? Well, there's a complex number that's not a real number. What is the standard complex number, let's say, that is not a real number? I. So, proof by contradiction. Suppose C is ordered. Huh? Then either, so I is something weird. Well, then either I is positive or it's negative, right? So either I is bigger than or equal to 0, or um, I is less than or equal to 0. Which of those six properties tells us that either 0 is less than or equal to I, or I is less than or equal to 0? Ah, by 4. So we gotta do two cases. So case one, what if you think, hey, I ordered the complex numbers and my I turns out to be positive? Okay, let's see. I'm going to use all these properties to come up with a contradiction. We begin by, I immediately have a positive number, so I can multiply both sides of an inequality by a positive number. I'm going to multiply by I. So 0 times I is less than or equal to I times I. Which property says I can do this? Six. You can multiply both sides by a positive number. Okay? And then we just simplify. 0 times I is 0, and I times I is -1. Okay? Now I want to move my -1 to the other side, so I add 1 to both sides. Which property says I can do this? 5. 0 plus 1 is 1. -1 plus 1 is 0. So 1 is less than or equal to 0. But we've already proven that 0 is less than or equal to 1. That was the previous result. In any ordered field, 0 is always less than or equal to 1. So we came up that 1 is less than or equal to 0, 0 is less than or equal to 1. So one of these properties tells us that 0 is equal to 1. Which property was that? property 2. And that's a contradiction. We're not done yet. But what that means is that if somebody would be able to order the complex numbers, I cannot be positive because I 0 less than equal to I leads to contradiction. So what if it's the other one? So what if I is less than equal to 0? Now we do the same. We add the opposite of I to both sides. We can do this by property 5. You can add the same thing to both sides. Then you get 0 less than or equal to the opposite of I. I got my positive number. So now I'm going to multiply both sides of this inequality by the positive number opposite of I. So we get 0 times the opposite of I is less than or equal to the opposite of I times the opposite of I. And that is by property 6. 0 times the opposite of I is 0. What do you think that the opposite of I times the opposite of I is? Opposite of I times opposite of I is not 1. What should happen to those two negative signs? They cancel out. So we get I squared, which is negative 1. And now you might say, oh, we already done this. Now you can just go over here and you get a contradiction. So we just can't do it. Whether you try to make I positive or negative, you keep running into contradiction. You cannot order the complex numbers. So you don't need to memorize the definition of an ordered field, just the meaning of it, meaningful inequalities. But so of the 3 standard examples of fields that we have, the rationals, the reals, and the complex numbers, the rationals and the reals are ordered. The complex numbers are not ordered. So that means do not write down inequalities involving complex numbers. So, for example, 2 plus 3i is less than 7 plus 5i. Don't write that down. It does not make any sense. We won't have our standard rules of inequalities when we do that. So that is one of the very big differences, or the biggest difference between real numbers and complex numbers. The difference between rationals and reals, that's a much harder. But real numbers and complex numbers, one is ordered, the other one is not. So let's have a look. There's 3 questions from the cset I could find. Let's see what they are about and what we can do on that. And then we're done. So cset 9, 10, and 11. Let's do 9 and 11 first. 9. Which of the following statements refutes the claim that GLR3 which is the set of 3 by 3 invertible matrices, is a field. It's very similar to the 2 by 2s. 3 by 3s, 4 by 4s, they all have the same properties. So they're saying that GLR3 is not a field, and which of those answers would be a proof, a reason why GLR3 is not a field? Is it because there exist elements A and B such that AB is not BA? Or there exist elements A and B such that the determinant of AB is the determinant of A times the determinant of B? If A is an element of GLR3, then there exists a matrix A to the negative 1, such that A to the negative 1A is I. And if A is an element of GLR3, then there exists a matrix A, such that the determinant is not 1. That last statement D doesn't make any sense, but it's part of the answers. Okay, so it's a little bit harder, this exercise. You got to read every answer and think about what does that say. And then, does that mean it's not a field? So what does property A's or answer A say? There exist two matrices such that AB is not BA. So what does that mean? AB is not BA. The multiplication is not commutative. Does that prove it's not a field? Well, the question then would be, in order to be a field, does your multiplication need to be commutative? For a field, everything had to work out nice. So here, this is needed for a field, so that would immediately make this the correct answer. Yeah? Your multiplication is not commutative, hence you're not a field. And so the nice thing is that the others you don't even have to check anymore. Proper answer B has nothing to do with being a field or not. It's a property, but it's not needed for a field, and it doesn't show it's not a field. Maybe a quick look at answer C. If A is an element of GLR3, then there exists a matrix AN negative 1, such that A negative 1A is I. What is answer C saying? Which property is that related to? Ever? There's a multiplicative inverse. There are inverses. But that is needed for a field. So this doesn't show it's not a field because it's needed to be a field. So that's why the correct answer here is A. Let's have a quick look at 11 and then spend our last 10 minutes on 10. Question 11. Which of the following sets is an ordered field? Complex numbers, rational numbers, integers, or the natural numbers? Correct. So the answer is not A. That is, the standard array is not an ordered field. Why is the answer not C or D? because these guys are ordered, but they're not fields. There are no inverses. Okay, so B, C, and D are ordered, but not all of them are fields. A is a field, but it's not ordered. So you really have to get the distinctions there. Okay, let's have a look at question 10. So this is about the complex numbers, and it is given that it is a commutative ring with a multiplicative identity that is 1. Okay, so let Z1 A plus BI be a non-zero complex number. It can be shown that C is a field if there exists a Z2 X plus YI satisfying the following equations. This question requires you to first think, what is going on here? Okay, so they're telling us it's a commutative ring and it has an identity. And we basically need to prove it's a field. Which property are we still missing in order to be a field? If somebody says you're a commutative ring and you have an identity, what are you still missing? So at this point, the complex numbers are one property away from being a field. The 5 properties are associativity, check, that's done. Closure, done. Commutative, that's given. Identity, that's given. We still need inverses. Now, they're not asking us to prove it has inverses. We know it does. But what they're saying here is that one of these answers implies that we have inverses. Well, what would it mean that Z1 and Z2, that Z2 is the inverse of Z1? What would be the definition of that? So here we want Z2 to be the inverse of Z1, which means when we multiply them, we should get 1. They're not telling us find out what Z2 is. They're saying what are the equations you would get? Well, A plus BI times X plus YI should be 1. We know how to find it, but could we set up maybe different equations for X and Y? What do you get when you FOIL this out? So we get an AX plus AYI plus BIXXI plus BYI squared is 1, but I squared is -1. So the real part is AX minus BY, and the imaginary part is AY plus BX. Ooh. When are two complex numbers the same? So now we're getting some equations almost. We just need to set the real parts and the imaginary parts are the same. Well, the real part on the left is ax minus by. What is the real part of 1? 1. The imaginary part on the left is ay plus bx. What is the excuse me, the imaginary part of 1? 0 is 1 plus 0I. So we have our two equations that they were looking for. Now you can write this in matrix form. Gotta be a little careful. My second equation is not written down nicely. I should have written it as bx plus ay to first have my x and then my y. So let me rewrite this as ax minus by is 1 and bx plus ay is 1. You can write this as a matrix times xy is 1, 0. Ooh. What does that first row need to be? So how would you work this out? Whatever's here goes times x, plus whatever's here times y, and I should get ax minus by, so that should be a minus b, ax minus by. What should be the second row? We got uh, the second row, sorry, there's no minus here. It's over here. It's the b for the x and the a for y. So the answer is D here. Not an easy exercise. We need to know a lot of stuff here. What are we looking for? Inverses. They're not asking what's the inverse of a plus bi. This is kind of another way to possibly come up with the inverse, but it's a very unpractical way by solving these equations. Okay, that's it for this workshop. We always have to do the hardest, the most abstract part last, but there's nothing to do about that. So tomorrow I will email you guys some exercises, or maybe already tonight, and the answers to day 7 exercises. And then in a couple days next week, I will email you the solutions of this. So that's it. Keep in touch. If you take the cset 1 exam, let me know how it goes and if I need to change anything on these workshops or not. The cset 2 workshop, if you signed up for it, will start sometime in July. So same thing as this one. A week before we start, I will send you guys an email with the links and so on. So unless any of you guys have any questions, that's it then. Are some of you guys taking the cset 2 workshop? Okay, so then I will see some of you guys in July for the cset 2 workshop. So have a great summer, and I will see you, some of you guys, then in 5 or 6 weeks. So.